Joining us today, we have Dr. Stephen Frautschi. Dr. Stephen Frautschi received his bachelor's in physics from Harvard University and then his PhD in physics from Stanford University. He has been an NSF Fellow at Kyoto University, a research assistant at UC Berkeley, assistant professor at Cornell University, and a visiting professor for the University of Paris and Pohang University in South Korea, and CERN in Geneva, Switzerland. He has been teaching at Caltech since 1962. He has written several significant publications and has won numerous awards. Thank you for joining us today, Dr. Frautschi. So for the first question, we wanted to ask, how did you get into physics?
Well, when I was a little boy, my father and mother gave me a book. I particularly remember one called Stars for Sam, which was astrophysics for kids. And they also gave me another book by Alfred Wegener about continental drift, which Wegener had, like many people, had noticed that the west side of Africa fits into the east side of South America and the Caribbean. But he'd gone further and noticed that the rocks were the same on both sides and the fossils were the same on both sides. So he hypothesized that the continents had moved, but that was actually not fashionable scientifically. People could not figure out how the continents could move. But later it was shown that Wegener was basically right, except it's tectonic plates that move, not whole continents nowadays. When I was in 7th or 8th grade, my mother took me to an office in downtown Madison, Wisconsin, where I grew up. This was a career advice person. And he asked me what were my likes and dislikes. And then he asked me what did I want to be when I grow up. I said either a businessman like my father or scientific research. And then he put together my likes and dislikes with my answers and mentioned that all my likes and dislikes were fit perfectly with scientific research and not with business. So that would give that advisor an A+. I used to take long walks with my dad, and on one of those walks he told me that, this must have been 7th or 8th grade, that physicists could explain, or at least had the raw material for explaining almost everything that happens in the natural world with just a few mathematical equations. And I thought that was extraordinary. I still think it's extraordinary. It is extraordinary. But that was part of what oriented me towards physics specifically. And in high school, I actually liked the biology class better than the physics class, but I knew that physics was full of mathematics, which I also liked, and biology didn't have much math at that time, as much more now. So with this background, by the end of high school, I was ready to major in physics.
So how did you prepare for your career and get started in research in physics?
Well, the first step in preparing for a career, of course, is to take a bunch of courses in math and physics, which I did at Harvard University. Probably half of my courses there were math and physics. Freshman physics at Harvard, I ran into trouble. Thought I understood the math, I thought I understood the physics, but I had trouble putting them together, which is pretty common. So on the second quiz, I had 2 out of 10. On the midterm, I had 63%. So I was wondering, do I need to find another subject? But I decided to knuckle down and give it a last try. So I worked all the unassigned homework problems in the text. That got me over the hump somehow, that extra practice. So by the end of the course, I was steady A. I never had as much trouble later in any subsequent course as freshman physics. So then I go to Stanford for graduate school. Now you have to make some decisions, what to specialize in. And a first decision for physicists is it theory or is it experiment? And for those who saw the Oppenheimer movie, Oppenheimer in England as a student soon realized he wasn't cut out for experiment, and I wasn't either. But you might ask, what does a theorist do? Well, an experimentalist, of course, makes equipment and conducts experiments with equipment. But a theorist, well, what you do all the time is make calculations, of course, how to make better equipment, how to use the equipment, how to do the experiments or compare with them. Can we extend the theory to new regions and so on? Now that sounds kind of cut and dried, almost like homework. So is there any creativity involved? With homework, a professor is telling you what the problem is. whereas in research, you are deciding what the problem is, what equations to use. So that's creative. And then another activity of theorists is making models. In other words, taking a complicated situation, dropping out some less essential features so you can understand qualitatively why things happen the way they happen. Astronomers in particular do this all the time because the stars are complicated and they're not in the lab. We can't control them. So they have to make models. And of course, that is definitely creative. And then there's the very high level, like Einstein, who makes new equations or resolves paradoxes of the old theories and so on. Physicists or scientists in general doesn't get to do that, but if you're lucky, once in a while, something that deep comes up. So I decided to do theory. What specialty in physics are you going to? I chose particle physics, elementary particle physics, the physics of electrons, photons, protons, these days quarks, and so on. And that's also called high energy physics because you need a lot of energy to make more massive particles or to explore how they react with each other and so on. So that's what I studied at Stanford. What my professor had us do, he put me and another student together on a calculation of something in quantum electrodynamics, which was a well-established theory by that time. We were calculating what should happen in an experiment at the Stanford Linear Accelerator, which accelerates electrons to high energies. SLAC for short, Stanford Linear Accelerator. So we worked on that. The experiment was done. The result verified quantum electrodynamics to a smaller distance than previously by a factor of 3 or 4. So that was my PhD thesis, or the gist of it. So that was kind of normal science, where you make small advances, not giant leaps forwards like Einstein, but almost all the time that's what scientists are involved in, incremental improvements in the theory, the experiment, and so forth. The conceptual tools one needs to do high energy physics include quantum mechanics and Einstein's theory of special relativity. These are hard to explain, both because they go beyond common sense, what we learned when we were young. Special relativity theory deals with speeds up close to the speed of light, and things we do in daily life, baseballs and so on, cars, don't move that fast. Quantum mechanics deals with very small things that we can't even necessarily see with our eyes. And at these different regimes, strange and queer things happen. One of them, of course, is E equals mc squared. Mass is a form of energy. Another one is that particles like the electron can also be viewed as waves. In fact, that's true of everything. Light can also be viewed as particles, photons, and so on. So I'll start with a red wave, which is of light, which is a pretty long wavelength. And then I'll add to it a green wave, which is a shorter wavelength. And somewhere in this long chain, they peak up at the same point. And I'll make that right here. So here's my shorter wavelength green light. And then I'll draw a blue light, which is still shorter wavelength. All of these add up in this point in the middle that I've drawn. And they tend to cancel on the sides. Now, of course, that cancellation isn't perfect, but if I add a lot more wavelengths, it's possible to make them completely cancel over on the sides so that we end up with something like this, which is called a wave packet. And each of these waves is moving, and therefore the whole wave packet is moving. So this conglomeration of energy looks like a particle, even though it's made out of waves. Okay, so that's the basic insight in this part of quantum mechanics. By the way, it's also practical. You probably have a bunch of handheld devices with digital technology, And the digits are little packets of energy like this, moving along down the wire or through the air. And of course, we all want as much information packed in as possible, so that we want narrow wave packets, and that involves using more wavelengths, which is called broadband, and so on. So this is both crucial everyday technology as well as concepts. That's the first calculation I made for my PhD, really acting as an apprentice. The professor knows more than I do at that stage. Now, after my PhD, so far, I've been moving in a straight line. I was learning more and more physics. I was learning how to do research. But at this point, I took a detour for a year. In college at Harvard, I'd taken a lot of courses in Western civilization, Western history, literature, arts, so forth. But I also took a full year course in the history and civilization of the Far East. That's what the faculty called it. The students called it rice paddies. Focused on China and Japan. And the Japan half was taught by Edwin Reischauer, who had grown up in a missionary family in Tokyo. So he was fluent in Japanese as well as fascinated. And he taught this wonderful course. And I was so interested in that I then, in my first postdoc, I went off to Kyoto, Japan, to the Institute for Fundamental Physics in Kyoto. Why Kyoto? Well, first of all, Hideki Yukawa was there. He had been the first Japanese winner of the Nobel Prize. And secondly, I knew that Kyoto was the ancient capital full of temples and gardens and wonderful scenery. So I went to Kyoto, and I think I should explain how did Professor Yukawa, what did he do to win the Nobel Prize? Now, in high school, you learn that the electric force falls as 1 over distance squared. Same as the gravitational force, actually. But to a high energy physicist, particle physicist, this is what the electric force looks like. The charged particles come along, that's these solid lines. They exchange a photon, which is the quantum of electromagnetism, and so they get scattered into a different direction and so on. Either attract each other or repel each other depending on their charges. Okay, now for the particle physicist, the reason this falls as 1 over distance squared when I convert it into a force is that the photon has a zero mass. Now, in the early 1930s, people discovered the nucleus of the atom, and there it was much smaller than the atom, and the nuclear force was evidently much shorter. It did not go as 1 over distance squared. It was much shorter range, and was somehow confining the nucleus. And Yukawa in 1935 explained that in these same particle terms as, so let's say we have a proton moving this way and a neutron moving this way. And he had them exchange a meson. This was his picture. The key thing about the meson was that if it had a non-zero mass, then the force was shorter range and in fact fell exponentially with distance from the source, whichever particle is our source. And from the approximately known size of the nucleus, which meant the approximate range of the force, he could deduce the mass that was exchanged, approximately. So he made that prediction in 1935, and eventually it was verified in the cosmic rays by looking at what happened with cosmic rays, and later with particle accelerators controlled in the lab. The mass was in the right range for Yukawa's prediction. So in 1949, he won the Nobel Prize. The prize caused the Japanese government to create this institute in his honor in Kyoto. So I was there for a year. I learned new physics, fascinating time in Japan, came back, and my next experience was 2 years as a postdoc at UC Berkeley. And there I was fortunate enough to work with Professor Jeffrey Chu, who was not Chinese, by the way. His name is spelled C-H-E-W. His father came from England. And Stanley Mandelstam, who was a brilliant postdoc from South Africa. And we were working out implications of some work that Mandelstam had done, actually. And Chu was a great group leader. He had a whole bunch of students who were working on different aspects of this. An important problem we focused on had to do with what's called spin. Now, spin is related to angular momentum. It's a form of angular momentum. Quantum spin has special rules. It's not a continuous set of possibilities like in angular momentum. It's quantized to integer values, which for Yukawa's mesons were 0, 1, 2, 3, and so forth. Yukawa's original meson was spin 0, and that worked fine. It didn't create any problem. But there was a problem in theory, if you exchanged a higher spin than 1. If you exchanged spin 2, 3, etc., the force grew rapidly with energy. And the higher the spin, the more rapidly the force grew, whereas experiments didn't behave that way. So something was wrong. And to tackle this problem, we noted that in the early 1960s, these higher spin particles were being discovered. The particle accelerators in the lab had gotten good enough so they could make these higher spins. So we noticed that the higher spins tended to come in families of excited states, spin 1, 2, 3, and so on. Progressively higher spin, and with the higher spin, they had higher energy. And according to Einstein, the higher energy meant they had a higher MC squared. Okay, so we made plots of spin. Now, shortly before this, an Italian physicist named Tullio Regge wrote a theoretical paper that there was a mathematical object that interpolated smoothly between these physical states of spin 1, spin 2, spin 3, and so forth. And this we called a Regge trajectory. I should go through the spins, the physical spins. So this was a Regge pole, we called it, and the movement of the pole we called a Regge trajectory. And then we made the crucial step of saying, okay, if we exchange any individual one of these spins with more than higher spin than 1, it grows unacceptably with energy. But let's exchange the whole family represented mathematically by the Regge pole. And in doing so, there's a region down in our left corner here where the spin is less than 1. And remarkably, that's the region that actually controls the force exchange between the particles. I won't be able to explain how that works. That was a contribution of Mr. Mandelstam, really. So we had solved the problem, which was this, that the force grew too rapidly with energy. And beyond that, down in the physical exchange region here, we had a spin less than 1, which meant the force would get weaker. It got stronger above 1, but it got weaker down here, and we could predict how much weaker. So we had a new kind of prediction for experiments, which in some cleaner cases worked. That was a very gratifying breakthrough. It earned me my professorship at Caltech. Now, later, other people, not me, not Mandelstam, not Chu, made, this is pretty abstract. Later, other people made tangible models of this and showed that if they considered each of these physical states to be a quark at each end with a gluon string in between, they could get the same results. So that was a new interpretation. And of course, we'd always thought of particles as little balls or points. And here we say they're strings. And later, a whole nother set of people went back to abstraction again, didn't need quarks or gluons, but came up with strings that actually incorporated gravity, a huge step forward. So that's the modern string theory. Very abstract, very hard to, it remains controversial because it doesn't explain enough data yet, but it's our best attempt to bring gravity into quantum mechanics in a satisfactory way. The excited states on these strings were higher oscillations. So you'd have a ground state, first excited state, second excited state. This is like vibrations on a string was the point of view about what were these excited states. And there's lots of young people working hard on this all over the world. Pasadena, Munich, Tokyo, Moscow, every place. Beijing, I'm sure. That's the unexpected offspring of this work back in the early 1960s. We had no idea we were working on strings. We just followed the data plus a set of ideas. So that got me to Caltech. Since then, I've been at Caltech guiding students in research. Eventually, I got to teaching undergraduate courses. And I've been here 60 years. The last 2 decades, it was mostly freshman physics. I still understand that much. Of course, that's a different style from high energy physics, but it has all sorts of contacts with everyday life.
Yeah, what are some of your teaching experiences? How has that been for you?
Well, of course, it's very gratifying when your students go out into the world and are successful. In teaching, I've tried to, of course, be clear, enable them to understand what they want to learn about. I've also found it helpful to inject little stories. Okay, so let's write down a couple of names of former Caltech students. I mentioned David Ho right at the beginning of the freshman year. Some freshmen want to know, let's say they're going to major in biology. So why do I have to take all this math, all this physics, as well as chemistry and biology, which I understand is going to be relevant to me? So I tell the story of David Ho. So he was a immigrant from Taiwan, one of the many immigrants who contribute to our country. And he was an undergraduate at Caltech. He majored in physics. And then he moved into biochemistry and medical research. At the scene when the AIDS epidemic hit, doctors came up with some medicines, but the viruses were very clever in mutating and defeating those defenses. The next idea was, well, let's use several different medicines. What was going on was a race between each antivirus in killing the virus and the changes in the virus to defeat the, the medicine. And rates of change are the subject of calculus, differential equations. So Ho took, it's a very simple set of differential equations, I understand, plus the data they had at the time, and put that together to make the AIDS cocktail, which has saved so many lives. And so with that accomplishment, he was sometime in the 90s, he was actually Time Magazine Man of the Year. He treated people like Magic Johnson. Now, of course, there were other well-trained, equally good biochemists working on this problem, but they hadn't been educated at the same time with calculus and differential equations as they have that point of view to attack this biological problem with those tools. Okay, so that's an explanation of why or an example, poster boy, of why we force our freshmen to take all these different science and math courses. Jim Hall, he was on the cover of many Popular Mechanics, even Newsweek. So what did he do? He was a race car enthusiast. He in fact won some national road races. But then he got interested in improving his cars. One of the problems in racing is you got to go around the corners and you have to slow down to avoid skidding. So you need friction. Friction, for some cases, is bad, but for going around corners, it's necessary. The force of friction is the coefficient of friction, as you learned in high school, times the weight. So he looked at that and scratched his head. Haven't we forgotten something, namely the air pressure pressing down on the car from above? 15 pounds per square inch. Why don't people talk about that? Well, the answer is because there's air pressure from beneath the car, almost exactly canceling from below. But that gave him the idea, let's create a partial vacuum under the car. And it doesn't have to be very good to make the car corner better. So he and his team of just 5 or 6 people re-engineered their race cars, create partial vacuums under the car. And his cars won the Indy 500 2 times. And then everybody else copied it. And now the leading teams have like 50 engineers working on it. Along the way, he had to create measuring devices for where's the pressure on this part of the undercarriage of the car. And he, of course, he'd learned all that in his mechanical engineers at Caltech. So those were a couple of examples of where things can lead.
You mentioned you've traveled and worked in Europe, Japan, and Korea. What was your
Switzerland.
experience in Switzerland? That's right.
Where the name Frautschi comes from.
Exactly. What was your experience like working with an international community of scientists?
Well, that's one of the real benefits of a science career. You often get to work in a foreign country and live there working with native people, not just the staff of the Hilton Hotel or something for a tourist. So that's a wonderful feature. These days, almost all publications are in English, so that's not so critical as it would have been in the past. Just to live happily in a foreign country, of course, it helps greatly if you can at least speak some French or German or whatever the local language is, and learn about different ways of life. Yeah, so that's a great benefit of this science life.
That's great to hear. And I know you mentioned some names already, but any that you wanted to note that you've had the chance to meet or work with?
Many, of course. Just at this moment in time, I should mention Oppenheimer, because obviously there's been a hit movie about him. Plus, he's such an important historical figure, not only in science. My last year at Stanford, he came and gave a public lecture, and it included the fact that you need to maintain different points of view in your mind. And he mentioned the particle and the waves. He didn't draw this diagram, but he mentioned that. It was mesmerizing. But then that evening, our professor wonderfully invited us, postdocs and his grad students, over to his house, and we sat around in a circle with Oppenheimer, chatting. A few years later, when my scientific research was well known, there were 2 times I went to a meeting and Oppenheimer was there, and normally a famous elder, like Oppenheimer was then, would hang around with the other famous elders. They know each other, they're comfortable there. But Oppenheimer would go, and he sought me out and a couple of other young guys, and wanted to know, what we were doing that was new that he didn't understand. He was perfectly ready to admit he didn't understand it yet, and I thought that was a big positive for Oppenheimer.
The PWPA founders, Dr. Sun-Myung Moon and Dr. Hak Jahan Moon, have said that majority of scientists have made it their mission to aid progress toward a happy, ideal society. That is, scientists develop science and technology with a keen sense of mission to actualize the dreams of all people. Sometimes men of power misused the results of scientific research for unrighteous purposes. And still, the fundamental spirit of scientists has aimed toward the fulfillment of an ideal society for humanity. So on that note, was there any message or advice that you would like to share with future and current scientists?
Well, first of all, you hopefully do have the opportunity to go out and teach young people to go on and develop new things that help people. I would say it's important to do something, find something, if possible, that you love to do, because there's going to be hard patches where you just have to grind it out. You get over the hard patches easier if you love what you're doing. Obviously, we're working hard on finding sources of energy that are less destructive, and that's critical to maintaining medical research. Well, we're going to get much more personalized medicine, like with cancer. Cancer has many different diseases, and you need specific treatments. And I heard a talk on that the other day. Caltech biology lady, Barbara Wold, W-O-L-D, has been working on this for years, developing a library of all the different forms of cancer. And this is on computers now, of course. And then separately developing a library of different treatments, ever growing, of course. And to get her library of different cancers, she had to, Caltech doesn't have a hospital, but she had to make connections, cooperations with all the hospitals in the area to bring in these different information on these varieties of cancer. And that involves computer scientists as well as the biologists and biochemists, of course. But that's one thing that's coming, except is it going to cost $1 million per treatment? Computers are going to help by speeding up the analysis and by automating as much as possible of the connections between the drugs and the different forms of the disease.